Dear students, welcome to another session on electrical machines. Today we are going to see about a DC motor. What is the power flow diagram and what type of losses the DC motor has. So before starting, I will just try to summarize what we have seen in the last class. For example, in the last class we have discussed about a machine which is of 5 kilowatt 200 volt DC separately excited motor, and we have told that the armature resistance RA and the field resistance RSH can be estimated. When we say about the field coil resistance, it is the resistance of the coil. The external resistance which is added to the field coil in series is not considered. Only the field coil resistance we can estimate the values of these two. And in which range does it fall? The armature resistance of the machine is usually very small, in the order of 0.3 to 0.5 ohms, where the field coil resistance will be in the order of hundreds of ohms. Alright, so there is a large difference in the armature resistance and field resistance. Now we have to find out the efficiency of the machine. Generally for a DC motor we say 75%, 80% efficiency. How do you really find out the efficiency of a machine in a deterministic method on the basis of calculation? So for that it is very much useful for us to analyze the power flow diagram and to understand the various losses happening in a DC machine. So as I told already, we are considering a DC motor. Alright, so the power flow diagram, let us go to the power flow diagram of a DC motor. I have shown the diagram of a DC motor in the red ink, if you can see, which is just a very simple diagram where you can understand there is a field, a shunt field and an armature circuit. To the shunt field we are giving a voltage Vf, and to the armature circuit we are giving a voltage Va, where F represents the field and A represents the armature. Generally Vf will be equal to Va. We just give the voltages separately, but the magnitude of the voltages which is given to the shunt field and to the armature will generally be same. So let us look into the power flow diagram. In the power flow diagram, the power which is going to the motor is given as P in total, the total power which is absorbed by the motor, which is obviously there are two circuits which is shown, field circuit and armature circuit. The power of the field circuit and the armature circuit, so which is Vf If. We know power is V into I, so Vf If plus Va Ia. So once the power has been absorbed, then there is a loss. In the first stage itself there is a loss due to the field coil, because field also has a resistance, we said in the range of hundreds of ohms, already we discussed. So field copper loss will be there in the machine, so If square Rf. This field copper loss need to be deducted from the P in total, which is also equal to Vf into If. Right, now what is left in P in total? Only Va Ia is left. So moving to the inner part of the motor, now Va Ia is the input. From there we have to again deduct the value of armature copper loss, because we know that armature also has a resistance, even if it is very small in value, but there exists an armature resistance, hence there will be an armature copper loss. So from VA we have to again subtract Ia square Ra, which is the armature copper loss. Now what will be the result? The result will be the gross mechanical power developed. Okay, in the armature. Where does it develop? In the armature. In the armature there develops a gross mechanical power. From this particular power again we have to reduce or subtract losses which you call as a rotational losses of the machine. Now this rotational losses has three different components. One is friction, the second one is windage, third one is eddy current loss in the armature. So frictional loss, why does friction loss happen in a DC machine? Obviously you know that there are parts like armature conductors and the bearings. All these things will rub each other and there will be a loss. This is what you call as a frictional loss. Alright. Windage loss is due to the air friction, air resistance. Okay, and there is a third loss which is an eddy current loss in the armature. So we will see after I say about the equation of efficiency, we will come back to this eddy current loss. Now once you subtract rotational losses also from the gross mechanical power, you get a shaft power which is the net mechanical power output. So the total input was VFIF plus VIA and the net mechanical power output is gross mechanical power developed minus the rotational losses. So this is just the flow diagram, power flow diagram. We haven't explained anything much in equation. We will come back to it at a later stage of this lecture itself. Now how can we calculate the efficiency of the machine? Efficiency is generally, the formula is efficiency is output divided by input. Here output is the net mechanical power divided by the net input power. Correct? P in total. So which is written here, you can see that. Right. This is written here. Fine. Alright. Now in a DC machine all currents are DC, which we know that, right? So in small machines we say like mostly the stator is made up of a solid iron, a single iron piece which is cut into whatever structure we require. Correct? A solid iron piece as shown in this particular diagram. See here the diagram is shown, so you can understand this particular diagram. Okay. Now suppose what happens if the rotor armature is also made up of a solid iron? Then the problem is that eddy current losses will appear in the rotor. So now you may ask a question that the stator is also made up of a solid iron, but in stator there is no eddy current loss. If the rotor is made up of solid iron, how in the rotor alone eddy current losses will happen? Definitely there is a clear reason. In the stator, what is the supply given to the stator? It is a DC supply and there is no other changes to that DC. The stator is a stationary thing to which a DC current is being given and there is no alternating quantities in the stator. But in the case of rotor, if you observe, the rotor is a rotating structure. Alright, the rotor in its rotation is experiencing a stationary field from the stator, isn't it? So what happens is that the rotor will cut the stationary field and definitely there will be an EMF induced in the rotor, and if the rotor has closed paths, then definitely there will be a circulating current in the rotor which you call as an eddy current. So there is a possibility in the rotor because the rotor is rotating in the magnetic field, in the stationary magnetic field, isn't it? So this is the reason why rotor is experiencing an eddy current loss while the stator is not. So the iron body is moving in a steady field. Hence, if you pick up any closed path in the armature, it will sometime see the maximum flux, isn't it? And sometimes zero flux. The maximum flux when it is aligned to the polar axis. Zero flux when it is aligned to the magnetic neutral axis. Therefore, there will be induced EMF and hence some circulating current which you call as eddy current in the body of armature. And as the circulating current passes through the rotor, the armature, rotor is the armature of course, the armature will get heated up. Alright, that is why the rotor of a DC machine we cannot use a solid iron for rotor structure. Okay, so this is how the rotational, that is why eddy current loss has been added in the rotational losses in the case of a DC machine. Okay, so how does this particular rotor looks like then if it is not a solid iron? You can imagine so many thin plates with slot and teeth. You know, the thickness of this plate will be only few millimeters. Okay, and each plate will have a varnish coating to the plate. So if there are so many plates like that, all the plates where there is a perfect alignment to the teeth of all the plates, to the slot of all the plates, so that you get a longer teeth. If you are stacking together all these laminated plates to a height, to make a height, then that becomes the length of the armature. So you have to imagine in such a way that maybe in the later session I can show you a picture of that. Alright, so you have to stack it in such a fashion that all the teeth become aligned. All the slots become aligned so that you can get a longer slot. Okay, and it is screwed. Alright. So this is what you call as a laminated silicon steel structure. So a rotor of the DC motor is made up in this structure exclusively to reduce the eddy current loss. Alright, so it is very easy concept to understand. Now the thing is that as far as this DC motor armature is concerned, now whatever current produced is AC current, which you know that in the armature, because there is no, it is all induced. Induced is always AC, alternating. That is why there is a frequency, alternating current. That is why you are experiencing the eddy current loss. And so you should not forget that point also. Now, the eddy current depends on field current and speed. How do I say that? Because you think logically, why does this eddy current came? Eddy current came because there was an induced EMF. Why the EMF was induced? It got induced because of the movement of the armature, rotation of the armature, which is the speed of the armature, N, in RPS, if I say. Second thing is because of there is a magnetic field. It is moving in a magnetic field, isn't it? The magnetic field is created because of the field current which you give. So when you analyze, you understand that the eddy current is depending upon the number of poles, obviously poles which is excited by the field current, or the field current and the speed of the armature. So if these two are constant, then a constant eddy current will be developed in the armature. Right? If any of these two keeps changing, then the eddy current also will change. That is the point I would like to make here. So now you have to see this particular page, fourth page. Okay. So now let us understand the motor operation in a better way. Let us again consider separately excited motor, because which is what we considered before and a little simpler for you to understand also. So I have shown a diagram where field and armature is shown separately, and I have also shown a diagram where this is a circuit diagram, right? So EB is the back EMF generated in the motor, and VA is your applied voltage to the armature. Alright, and IA you have to mark always to this direction. Okay, in the generator it will come in the opposite direction. So normally to the field and to the armature we give the same supply. So VF is equal to VA. So generally what did we discuss in the last class in the principle of operation is that when the motor is just starting, the speed is very less and the generated EMF, the back EMF of the motor is directly proportional to the speed of the motor, because we know EB is equal to E is equal to phi SLN by 16 to P by A. So E is directly proportional to N, speed of the machine. So when N is very small, EB will be very small. When EB is very small, the current drawn by the motor will be high. This is a non-fact for us. And we know that the current will shoot up to a large value and gradually decrease after EB has been built up. Right, and settle to a value. The current will settle to a value. What is that final value to which the current gets settled? The current will settle to a value in such a way that a speed to a current value to the machine is actually will settle to a speed such that enough current will be drawn from the armature supply which will make the load torque equal to the electromagnetic torque. Did you understand the point? See to which value the armature current is going to settle after EB is developed. How do we find out that? That totally depends upon the load. So what is the load torque? To maintain that load torque, how much electromagnetic torque is required to develop by the motor? So the current will be drawn to such a value that till the electromagnetic torque becomes equal to the load torque. Alright. So when we can say that suppose the load torque is not there, you may ask a question, if there is no load, in that case the current must settle to zero, right? Because there need not develop any electromagnetic torque to supply the load, to meet the demand of the load. So ideally the current must fall to zero, but practically it will not. It will fall to a very minimal value which I have shown in this. This is the structure. Alright, so this particular graph shows that. Now what is the equation of back EMF which is developed? We know that phi is N by 16 to P by A. So I am taking only phi and N, rest all thing I am putting it as a constant K. So we can say that EB is equal to K into phi N for ease of understanding. Right. In this particular, from this particular diagram, we can understand that VA is EB plus IA into RA. Now multiply both sides of this equation by IA, then you get a very meaningful equation. See that you got an equation VA IA is equal to EB into IA plus IA square RA. So this is actually the power balance equation for a DC motor. Can you see that? VA IA is the input to the armature, isn't it? After the field copper loss, whatever comes into the armature, which is VAIA. This VAIA, the input power, is been spent as two factors. What are the two factors? EBIA, first factor, plus IA square RA. We are very familiar with this. IA square RA is the armature copper loss we have discussed earlier. Then what should be this? It should be the mechanical power developed, isn't it? The gross mechanical power developed as per our power flow diagram. You can just check here. See that after IA square RA is been deduced, what was here? It was gross mechanical power. So you understood that the gross mechanical power developed. So EB into IA. Now we got an equation form of gross mechanical power developed. Correct, very good. So now page number 3 you have to check gross mechanical power is EB into IA, isn't it? Now how can you find out the developed torque? How do you find out the developed torque? If power is there, power divided by angular speed is torque. This is also a known factor for us. So EB into IA divided by 2 pi n, where n is in RPS, right? Rotations per second. Now let us split this particular equation and write. I am taking 1 by 2 pi n separate, alright, and writing EB. EB is what? P into Z into A by phi n, that is K phi n. K value is P Z by A phi n into IA, isn't it? Since n is in RPS, the 60 and all will not come. IA. So you cancel out all n. Then what is there? P Z by 2 pi A into phi into IA. Now if you watch this equation very close, you understand this is the equation of what is it? Electromagnetic torque developed in the armature. So what do you understand from this? The gross developed torque is equal to the electromagnetic torque developed, which is Pz by 2 pi A into phi into Ia. Now we can calculate P net mechanical. What is it? The last part of the power flow diagram. What is it? The gross mechanical power developed minus the rotational losses. You can see here. Gross mechanical power minus the rotational losses, you get the net power, isn't it? So you get it as EB IA minus rotational losses. Rotational losses generally will be given, or when it comes to certain numerical problems we can again have an in-depth detail of how rotational losses can be put into equations, right? Generally the vintage, friction loss and all, they will give the value, correct, and the eddy current loss too. Now how do we exactly calculate an operating point of a DC motor? So we can see a practical example, a numerical problem, and try to understand. So I am redrawing this particular diagram here, the same diagram, and whatever EB, we had two equations. One is K phi n, and we have another equation EB, which is VA minus IARA. And if you observe, suppose V is in the order of 200 volt, the applied voltage to the armature, and the armature current is in the order of 30 ampere. Just an example I am saying. If the armature resistance is 0.5, so what will be the value of IARA? It will be 30 into 0.5, which is 15 volt. What is the applied voltage value? It is 200 volt. See the difference. Applied voltage is 200 volt, where IARA value is only 15 volt. That means there is a large difference between the applied voltage and the IARA drop. So most of the calculations or most of the analysis, since IARA is very much lesser compared to the applied voltage, it is neglected. It is just for the ease of analysis. If you want to have a very accurate analysis, you have to consider that value. But to this level of lecture, I am trying to neglect IARA for this particular numerical problem. So let us see how the whole operating point we can find out. Right, suppose there is a DC motor with an armature applied voltage initially as 200 volt. So VA1 is 200 volt. It is running with an speed of 1000 RPM, and it has an armature current initially 15 ampere. If IARA is neglected, according to the equation of EB is equal to VA minus IARA, EB is approximately equal to VA, because IARA is 0, we are neglecting. In the above case, EB1 is 200 volt, correct, because whatever is VA1, that is EB1. Simple. Alright. So now the next condition is that, see the page 5. If the armature voltage is reduced to half, initially it was VA1 was 200 volt. Now the question is that if it is reduced to 100 volt, then what will be the speed and what will be the armature current? How can you find out? And provided the TL is constant, that is the load torque is maintained constant. So first we know that armature drop is neglected. For that VA1 is EB1, VA2 is EB2. So we are rewriting that EB1 is 200 volt, EB2 is 100 volt, correct? And what is the electromagnetic torque equation? It is K phi into Ia, some constant into phi into Ia, which we already discussed, isn't it? So K phi, we don't know the value, which is constant. So K into phi into, what was Ia1? 15, we don't know the value of Ia2. And we know that electromagnetic torque is equal to the load torque, right, which we have just explained, and we have come to that conclusion here, isn't it? This particular part we have already concluded that. That is it. See here. Here we have said this electromagnetic torque is equal to TL. Hence we are putting this as TE1 is TL1, TE2 is TL2. And TL is constant, and here therefore TL1 is equal to TL2. That means that we have a chance of equating this particular electromagnetic torque equation. Correct. So now we try to make the fraction EB1 by EB2, which is 200 by 100. EB is K phi into N. So K phi into N1, we have to find N2. N1 is 1000 given in the question itself. So EB1 by EB2, which is 2 is equal to 1000 divided by N2. So what will be N2 now? 1 by 2 into 1000, which is 500 RPM. You found it out. Very simple. Right, now we try to take the ratio of TE1 and TE2. The ratio is actually 1. It should be 1 because TL1 is equal to TL2. So we try to equate it. 15 divided by Ia2 is equal to 1. That gives you Ia2 is equal to 15 ampere. Alright, so in the second step, if you want to find out the value of current, you can do and get this value mathematically like this. Otherwise, from the concept also you can directly write, because I have already told you if the armature current will change only if there is a change in the load torque, if TL changes. The question, it is clearly mentioned that the TL is a constant. TL doesn't change. Correct. Then whatever was Ia1 should be Ia2, because there is no change of value in the load torque. Okay, so I think I am supposing that this topic became clear to you. If you have any questions, we can discuss it in the classroom. Alright, thank you.